ChatGPT, Stable Diffusion, self-driving cars, completely different products, completely different companies, completely different problems, but all of them, every single one of them, is built on the same mathematical foundation. Not statistics, not calculus, not even probability. They're all built on linear algebra. And here's the thing, most people learn linear algebra the wrong way. They see through matrices, determinants, and eigenvalues, and they never understand why any of it matters. It feels like abstract nonsense with no connection to anything real. This video fixes that. By the end of the next 13 or so minutes, you'll understand what linear algebra actually is, how it works, and you'll see it running inside a real neural network. Hi, I'm Bishir, and this video is one amongst a complete free series, 23 videos covering every piece of math you need to understand modern AI, all built from scratch. Before we write a single equation, I want you to understand what linear algebra is at the gut level, not definition, the feeling, the idea behind it all. Here's a question. How does a computer see a photograph? Think about it for a second. An image for a dog, maybe. What does the computer actually have when it has that image? It doesn't have a picture, it has numbers. If your image is 28 pixels wide and 28 pixels tall, the computer has 784 numbers. Each one is a brightness value, 0 is black, 255 is white. Everything in between is gray. That's the whole image, just a list of numbers arranged in a grid. Now here's the question linear algebra answers. Once your data is numbers, how do you do things to it? How do you do things efficiently to it at scale? How do you rotate the image, blur it, detect edges in it, compress it, pass it through a neural network? Well, the answer to that is linear algebra. Linear algebra is the mathematics of organized numbers and the operations you perform on them. Well, the organized numbers, we call those vectors and matrices. The operations, we call those transformations. That's the whole subject. A vector is just a list of numbers. If I say move 3 steps right and then 4 steps up, that's just 3, 4. That's a vector. That's all it is. In AI, every data point you'll ever work with is a vector. A word in a language model is a vector. An image is a vector. A user's taste profile in a recommendation system is a vector. The entire input to a neural network is a vector. A matrix is a 2D grid of numbers with rows and columns. It's just a table of vectors. Your dataset of 10,000 training examples, that's a matrix. 10,000 rows, 1 per example. The learned weights inside every layer of a neural network is a matrix. Your image, if you stretch it out flat, it's a vector. If you leave it in its grid shape, well, it's a matrix then. And here's what makes this powerful. When you want to transform data, you multiply matrices together. One operation, millions of numbers transformed in one shot. That's why GPUs exist, not for gaming, for matrix multiplication. The operation is so fundamental to AI that we built specialized hardware just to do it faster. Linear algebra is the language AI thinks in, and right now you're going to start learning it. Alright, let's get precise. I'm going to cover the core objects and the core operations. Take notes if you want, but don't stress about memorizing anything. The Python section would make everything concrete. Let's start with a simple vector. V equals 3, 4. Or another example, V equals 1, 2, 3. A vector is just an ordered list of numbers. If it has two numbers, we call it two-dimensional. If it has three numbers, three-dimensional. And in general, if it has n numbers, we say it's n-dimensional. Now, mathematicians like to write this compactly as V belongs to Rn. This notation just means V is a vector containing n real numbers. Nothing scary, just a shorthand to save space. Now let's talk about the most important operation, the dot product. Let's take the vector u, which is equal to 1, 2, and the vector v, which is equal to 3, 4. Now u dot v is equals to 1 times 3 plus 2 times 4, which is equals to 3 plus 8, which is equal to 11. The dot product takes two vectors of the same length, multiplies matching components, and adds them up. But the real meaning is this. The dot product measures alignment between two vectors. If two vectors point in the same direction, we get a large positive number. If they are perpendicular to each other, we get 0. If they point in opposite direction, we get a negative number. This one operation is the heartbeat of deep learning. Every neuron computes a dot product. In short, the dot product shows similarity between two vectors. Now let's move on to magnitude. Let's take the vector v equals 3, 4. Now the norm or magnitude of v equals the square root of each element of v squared. So for this particular example, it will be the square root of 3 squared plus 4 squared, which equals the square root of 9 plus 16, which equals the square root of 25, which is 5. This is called the magnitude or the L2 norm. It measures the length of the vector. In AI, we use this constantly for measuring similarity between embeddings, words, images, user preference, etc. Now we move to matrices, which we've already talked about briefly earlier. Let's take the matrix A, which has in its first row 1, 2, 3, and the second row 4, 5, 6. This is a matrix, a rectangular grid of numbers as we've discussed earlier. It has 2 rows and 3 columns. We describe its shape as A is 2 by 3. Rows by columns, always in that order. If we want to refer to a specific element, we write A, I, J. That means row I, column J. For example, A12 equals 2, row 1, column 2. And A23 is the last element, which is 6, the element at row 2, column 3, again, which is 6. So let's move on to matrix multiplication. Matrix multiplication is the single most important operation in modern AI. We'll start with a concrete example, then we'll generalize. Let A be the matrix 1, 2, 3, 4. Let B be 5, 6, 7, 8. We're going to compute A times B. To compute the top left entry of the result, take the first row of A and the first column of B and compute their dot product. C11 equals 1 times 5 plus 2 times 7. That's 5 plus 14, which equals 19. So the top left entry of our new matrix C is 19. Matrix multiplication is just a dot product between a row and a column. We repeat the exact same process for the other elements in the matrix. C12 equals 1 times 6 plus 2 times 8, which is 22. C21 equals 3 times 5 plus 4 times 7, which is 43. C22 equals 3 times 6 plus 4 times 8, which is 50. So the result matrix C is 19, 22, 43, 50. Matrix multiplication is nothing more than many dot products organized systematically. Now notice something extremely important. The number of columns in A must equal the number of rows in B. A is a 2 by 2 matrix. B is also a 2 by 2 matrix. The inner dimensions must match. Now we generalize. If A is an m by n matrix and B is an n by p matrix, then A times B is an m by p matrix. The inner dimensions, the two n's, must match. The result keeps the outer dimensions. In our case, C keeps the outer dimensions. Inner match, outer survive. So if A is 2 by 3 and B is 4 by 3, the inner dimensions do not match, so it's not possible to multiply them. But if A is 2 by 3 and B is 3 by 3, the inner dimensions match, so they can be multiplied, and the result will be a 2 by 3 matrix. Let's take this matrix as an example. Can it be multiplied? The answer is yes. And this is the result. Since the inner dimensions match, it can be multiplied. And the result will be a 3 by 3 matrix. Since the outer dimensions are 3 and 3. 3 rows, 3 columns. The number of rows from the first matrix and the number of columns from the second matrix. One final operation for now. Let's take matrix A. 1, 2, 3, 4, 5, 6. The transpose of A, written A superscript T, is 1, 4, 2, 5, 3, 6. The transpose flips a matrix across its diagonal. Everything that was horizontal becomes vertical. Formally, A superscript T at ij equals A at ji. You'll see transposes constantly in backpropagation, embeddings, and attention mechanisms. We'll meet this concept many times in this series. Let's make all of this real. I'm going to implement everything we just covered, first from scratch in pure Python, then with NumPy, which is the library every AI framework is built upon. I want you to see exactly what's happening under the hood. We've got two vectors, simple lists. Now, the dot product from scratch. We zip the two vectors together. That pairs up the matching components. Multiply each pair, then sum everything up. That's literally all it is. 32. 1 times 4 plus 2 times 5 plus 3 times 6 matches exactly what we calculated on the board. Now the magnitude. We square each component, adding them all up. Then take the square root. Basically, the Pythagorean theorem. 5.0, that's the length of the vector 3, 4. Now matrices. I'm building the multiplication by hand so you can see what's actually happening inside. Three nested loops. The outer two pick the position in the output, row I, column j. The inner loop computes the dot product between that row and that column. Every single element in the result is just one dot product. 19, 22, 43, 50. Exactly what we got on the board. But notice what we're doing here. 3 loops touching every element one at a time. On a small matrix, this is fine. On anything real world, millions of parameters, this would be painfully slow. Which brings us to NumPy. Same math, completely different speed. NP dots, one function call, that's the dot product. Same answer, but NumPy isn't running Python loops to get there. It's calling optimized routines written in C and Fortran, running directly on your CPU's vector units. On large matrices, we're talking thousands of times faster than what we just wrote. And this, the at operator, is matrix multiplication in NumPy. One symbol, that's it. 19, 22, 43, 50. Identical results, one line of code. Transpose. Dot T. That's all it takes. Rows become columns, columns become rows. Shape tells you the dimensions. Rows, then columns. You will type dot shape hundreds of times, debugging models. Get into the habit of checking it constantly. And this right here, random.randn, is exactly how neural networks initialize their weight matrices. Here's where it all clicks. I'm going to show you exactly where everything we just learned lives inside a real neural network. Alright, this is where everything comes together. We've got an input, one image flattened into a vector of 4 pixel values. We set up the weight matrix and the bias vector for one layer, for layer 1. Then this line right here, W1 times X plus B1, that's a matrix multiply and a vector add. That is a neural network layer. One line, then we apply ReLU, which just clamps anything negative to 0. Layer 2 does the exact same thing. 3 neurons down to 2 outputs, 1 score per class, and that's your forward pass. Every single layer in every neural network ever built, GPT, BERT, ResNet, all of them is fundamentally doing exactly this: a matrix multiply, a bias add, an activation function, repeated, stacked, scaled up to billions of parameters. The math is identical to what we just covered. The scale is different. When researchers talk about weight matrices, that's linear algebra. When you hear embedding space or latent space, well, linear algebra. When you see attention heads in a transformer, linear algebra. When gradient descent updates the parameter of a model, it's linear algebra. Everything in this series builds on what you just learned today. Let me learn this. Today you learned 3 things. First, vectors. A vector is just a list of numbers. Every data point in AI, every image, every word in a language model is a vector. Second, matrices, a 2D grid of numbers. Your dataset is a matrix. Your neural network weights are a matrix. And third, matrix multiplication, the most important operation in all of AI. The inner dimensions have to match. Order always matters, and under the hood is just dot products repeated systematically across the grid. Then we saw all three of those ideas come together in 10 lines of Python, a real neural network forward pass built entirely from what we covered today. Next video, we go deep on vectors. Yes, just vectors. We'll look at dot products, norms, cosine similarity, and I'll show you the math behind word embeddings, Google search, and Spotify recommendations. It's one of the most beautiful ideas in all of machine learning, and it all comes down to a single operation you already know. If this helped, subscribe, like, and click that bell icon. The full series is free and we're posting every day. Drop a comment with your biggest question about linear algebra and I'll read all of them. I'm Bishir. See you in the next video.